divided into carbonaceous, ordinary, Murumuruti, and enstatite. So ordinary ones make around 85% of all the meteorites that we have. And my work is on carbonaceous chondrites. So meteorites are named after the place where they fall or where they are found. And the reasons why they are famous here is either they are scientifically important or there is just something circumstantial about it. So I and Murchison, two of my favorite carbonaceous chondrites, I'm working on them. They both fell in 1969 in opposite parts of the world, in Mexico and Australia. And it was the same year as the moon landing. We have tons of material, and they also happen to be two of the most widely studied meteorites. So what makes them special is that IND has calcium aluminum inclusions, which are the first formed solids in the solar system, and their age is considered to be the age of the solar system. Then Murchison has abundant hydrated minerals, amino acids, although they are of abiotic nature, and pre-solar grains, which are as old as 7 billion years. Then here you have India and Murchison, both look very similar. You can see the spherical chondrules, which are molten drops of silicates which have condensed from the solar nebula a few million years after the CAIs did. So here on the left of IND, you can see irregular CAIs. Then you have the Canyon Diablo meteorite. So the meteorite here is not that fascinating, but the effect that it left on Earth is. So it left the mile-wide Barringer crater in Arizona 50,000 years ago. We have around 30 tons of this meteorite recovered so far, and it's made of iron nickel alloys and some diamond inclusions. So ALH 84001 and ORGE. So the first one is a Martian rock. It's one of the oldest Martian meteorite that we have, but it's also notorious for its weird organic structures, which were thought to be Martian nanofossils. But then the wider scientific community just thinks that a lot of inorganic processes can also give rise to these organic structures. But the claim was so big that the then US President Bill Clinton announced it on national television. Then you have orge. It's one of the most primitive chemical composition. It comes from a rare group of carbonaceous chondrites known as CIs, and its elemental abundances are used as a standard against which we study terrestrial rocks. But it also has its own share of conspiracies. The story goes that you can see this plant-like structure on the top part of the sample on the right. So apparently someone prized the rock open when it was just sitting in the collection, planted some seeds in it. And then after a few years, scientists found this plant somehow coming out of it. And it was claimed that it was actually of extraterrestrial origin, but then it was soon found out that it was fake. And it also happened to be that this plant species is native to southern France, exactly where the meteorite was seen to fall. Then you have four ordinary chondrites with some extraordinary stories. The first one is the first meteorite to ever injure a human. There have been no deaths so far, which is great. Then we have the Valera meteorite. It caused the only known fatality in a cow. The poor cow died when the meteorite just fell on it. And then we have the Peekskill meteorite. It damaged the trunk of a car, and the value of the car just went up. And the Chelyabinsk meteorite, it was a superbolide which exploded over Russia in 2013. And here, this picture is from the Chelyabinsk meteor, which was witnessed by a lot of people. And it caused a lot of property damage because of the shock waves that it sent out. Then you have another iron meteorite. It's the largest known intact meteorite, weighing around 60 tons. And it was discovered in Namibia in 1920. And it's so heavy that nobody has bothered to move it. And it's now a national monument. Then black stones of Emesa and Kaaba, the first one in the 2nd or 3rd century AD. It was a cone-shaped meteorite which was worshipped as the Roman sun god Elagabalus by the Emperor Antoninus. And he was a bit crazy. He wished to marry it. I don't know how that would work. And he was so crazy that he was eventually assassinated, and the rock was returned back to Syria where it had come from. Then the Black Stone of Kaaba, it's the most sacred treasure of Islam. There is no way to know what exactly it is, but just by looking at it, people have made theories that it looks like a meteorite. But the most plausible theory, according to me, is that it's an impactite, which is a type of rock that forms when you have a meteorite impact, and it because of the high shock. By the high shock metamorphism and temperatures, you get this type of rock, but there's no way to know for sure. Then you have Henbury. It fell around 5,000 years ago, and it's in Northern Territory. And the local Loricha people recount it as a fiery devil which ran down from the sun and made his home in the earth, and he will burn and eat any bad blackfellows. So they kind of just stay away from these craters, and any water that sometimes accumulates in it was never drank by those people, saying it was contaminated with iron by God, obviously. Then you have the Ensisheim meteorite in 1492. It's the oldest recorded meteorite fall in recent history, and the people collected it and chained it up in church to keep it earthbound to gift it to the then King Maximilian. And finally, you have Mbale. It fell in 1992, just 28 years back. And the stones were thought to be a gift from God, and they were made into a powder and mixed with medicines in a hope that it will cure AIDS. So, some honorable mentions. You have lunar and Martian meteorites. Both are very rare and very scientifically valuable. Then you have the Tunguska event in 1908 in Siberia. Although we don't have a meteorite that was recovered from that event, it had huge catastrophic effects on the surface. A lot of trees were flattened and cattles were killed. And it's thought that it's a comet which exploded in the upper atmosphere, and it caused it did not leave any debris because it's full of volatiles. Then you have old iron meteorites used by the pharaohs to make tools that set off the Iron Age. And finally, the one that's probably the most famous one that killed or at least contributed to the death of the dinosaurs. So that's the last slide. Here on the left, we have an iron meteorite, which is worth almost 500,000 US dollars, and it was auctioned off at that amount in on a Valentine's Day auction because of its shape. And you have a palisade on the right. Because of its beautiful textures, the big pieces get sold off for over $1 million. And here you have olivine grains in green color embedded in a ground mass of iron nickel alloys. So that's all from my side. Let me know which one you found the most interesting. Thank you.
Thanks, Addy. That was really interesting.
Thanks.
Very different, but I really enjoyed it. Does anybody have any questions for Addy? We've got a little bit of time. Yeah, yeah, Kelly's right. It would make an awesome blog post. So
Yeah,
you'll
I would be
probably hit
happy
up.
to write up something on it.
Addy, can I ask about the rock that's the treasure of Islam?
Yeah.
Can anyone do non-destructive analyses on it to figure out what it is, or you're not allowed near it?
You just can't. It's too precious for the people, and you're just not even allowed to use it. Like even spectroscopy is not allowed.
Right. That's what
Yeah.
I was wondering.
Yeah.
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 Huh. It's interesting. Thanks.
Yeah. No worries.
All right. If no one has any more questions for Addy, might jump onto our next student talk, which is from Lou, and her talk is titled "Keeping an Eye on Melting Polar Ice Sheets from Space." Oh yeah, Lou. Oh, and just a quick one: our talk's being recorded, so if you don't want your video up, just turn it off before. Lou, I don't think we can hear you yet. It's your video.
are next to the... Hello? Can you hear me now?
I can hear you now, yeah.
Okay. Yeah, I'm sorry for that.
Okay.
Let me just share my screen. No. Okay, thank you very much for showing up today. I will be presenting what my research is about. I am on the aerodynamics group, and this is titled Keeping an Eye on Melting Polar Ice Sheets from Space. Now, did anyone see this headline on July from the Sydney Morning Herald that people were being evacuated from their beautiful mansions on Central Coast because the foundations of the houses are being eroded away? So since 1880s, we've been able to measure how global sea level has risen about 21 to 24 centimeters. And it was until the 90s that we were able to measure it more accurately through satellite data. And that also allowed us to break it down into what contributes, whether it's thermal expansion in the red line or the addition of water, which is the blue line. Now, here it says mostly meltwater, meaning that we have to build mass balance estimations from Antarctica, Greenland, or mountain glaciers. And we do this by looking at how much snowfall is coming into, for instance, Antarctica, and how much is it discharging. So if there's more snowfall than ice melting, then we have a positive mass balance, meaning that we're taking water from the ocean. But what is actually happening is that there's more ice being melted than the one coming in through snowfall, and it's reflected on this graph. So we're able to break it down into pieces to measure it in different ways. One of them is through satellite altimetry, which pretty much how it works is that we're able to measure very accurately up to a couple of centimeters the distance from the satellite to the surface of the Earth. And we also know the distance from the satellite with respect to the center of the Earth. And from that, we know the distance from the center of the Earth to the surface. And if we take measurements over decades and we're able to plot them, we're able to track how sea level is rising or how the height in the ice is changing. Another way on how we do it is through space gravity. How this works is that there's a satellite that will measure all the mass from the satellite to the center of the Earth. So the satellite, it will orbit responding only to the static gravity field, meaning mountains and tectonics. So what we specifically look at is at the temporal gravitational changes, which are for the most part caused by water, which we can see it in atmospherical changes, floods, ocean tides, snowfall, the melting of ice sheets, sea level, surface water, soil moisture, groundwater, and even earthquakes if they're large enough. So pretty much how it works, we can see it on this diagram. The satellites, they're in orbit and as they approach mass anomaly, which will be the ice on top of this mountain, the gravitational pull will make the first satellite accelerate until it passes the mass anomaly, and then the following satellite will accelerate as it passes the anomaly until it catches up with the first satellite. So what we look at is at the changing distance between the satellites, and we can model the changes that reflect the variations in water. So satellite altimetry and space gravity allow us to make mass balance estimations over Antarctica, and we can see it here. So both figures are very similar. In both of them, we can see that the highest mass loss is in West Antarctica. The spatial distribution is very similar. Now, what is different? We can see that in satellite altimetry, the figure is more detailed than the one from space gravity. This is because of the way it takes the measurements. The spatial coverage of satellite altimetry is very specific, and it will take very accurate measurements at a specific point. And as it orbits, it will take measurements separated every 15 meters. One of the limitations we have with satellite altimetry is that we have to make assumptions on how compacted the snow is, because the compaction of the snow will affect the height of the ice, but not the amount of mass. So we have to make snow compaction models as well as density assumptions, because we need to know the density of the mass that is either being gained or lost. Unlike with GRACE, we have a full coverage of all the area, and we don't have to make any assumptions on densities or snow compaction, because we already were able to measure out to a tenth of a human hair the amount of mass, whether it's gaining or losing. And they're very accurate. And from this image, you can see the resolution is of 300 kilometers. This is because if we were to try to get a final resolution, we wouldn't be able to rely on the estimations. It will give us a higher error. So if we were able to have a final resolution, it will require for the satellite to fly closer to the atmosphere, but it will also mean that it needs more fuel to continue to orbit, making the mission shorter. So since we cannot get a final resolution by changing how the satellite works, we have to look for different techniques to get a final resolution, which allows us to better locate where mass loss concentrates on glaciers. So that's what my project will be about, which is joining GRACE, which is the gravity, satellite gravity, and ISO2, which is the satellite altimetry, taking the full coverage of GRACE, but it doesn't rely on snow compaction models and density assumptions, and the detailed and accurate estimations of ISET. Now, as of right now, I started 6 months ago, so I don't have any cool results to show right now, but if you come back next year, I will. Thank you very much.
Thanks, Lou. That was really interesting and a great overview.
Thank you.
Does anybody have any questions for Lou? We've got a couple of minutes.
Oh, thank you, Marta.
Yeah, I agree with Josue. It's going to be really interesting what comes out of your project. I'm looking forward to your talk next year at StuCon.
Yes, I will. All right, I'll stop sharing, but thank you very much.
No worries. Okay. So next up, we have a talk from Jujier on gold solubility in magmas. Did you want to share your screen?
Hi, can you see my screen?
Yep, all good.
Yeah, thanks. Good morning. My name is Zhijie. I'm a second-year PhD student from Experimental Petrology Group. Today, I'm gonna talk about the gold solubility in magmas. We all love gold. I can't see a reason that people don't like gold, except for they are allergic to it. Gold has been used in many aspects of life since our early civilizations, such as jewelry, coinage, investment, electronics, medicine, etc. Under the huge demand, the gold price is rising over the recent years, as you can see from the diagram here. So I guess one of the missions for us geologists is to find more resources, but how do we find them? I would like to focus on the gold transportation part. As we all know that magmas are a proxy that can bring materials from deep down the earth to the surface. So we need to know how the gold behaves in magmas. If you imagine a boiling water, when I throw a tea bag and wait for 30 seconds, I can get a very nice cup of tea. What dissolves in the water during this process adds flavor to the water. If I have a choice, I prefer the tea rather than just plain water. So similarly, if we throw a piece of phase containing gold, such as gold metal or sulfide, into the hot magma, we can dissolve gold in magma as well. This equation shows the mechanism of how gold dissolves in magma, and it's allied with oxygen. To cook a cup of tea doesn't require a lot of techniques, but there are some critical factors that control the gold solubility in magmas. Over the last 30 years, many aspects has been studied, such as this. For example, the melt composition. People have found that the major composition of the magma can affect the structure of the melt, and it can play a role in the gold solubility. Also, some elements that has affinity to these elements to gold can increase the gold solubility, such as iron, sulfur, and chloride. Also, the temperature and pressure can affect the solubility of gold. In my research, I will focus on the oxygen fugacity and sulfur fugacity to see what's their role on the solubility of gold. It's quite clear that oxygen fugacity, when oxygen fugacity increases, the solubility of gold increase as well. But the role of sulfur is kind of under debate. Some of the researchers say the sulfur plays the role 100 times. I mean, it can increase the solubility of gold by 100 times. But well, let's see. It's not always easy to do this research, not only because the concentration of gold is quite low in magma, but also there's a problem that hinders we measure the concentration, that is called the nano nugget. The nano nuggets are artificial equilibrium products during the experiment. If you take a look at the picture on the right, this dendritic structure are the signal of quenched melt, and they grow from the nugget, which means the nugget are formed during the experiment. So if you do the analysis of the melt and you hit the nugget like by accident, you will overestimate the concentration of the melt, which can give you trouble. So the reason the nugget formed is because of the oversaturation of the metal. It's, as I said before, the oxygen can increase the solubility of gold. In the beginning of the experiment, if you have higher oxygen fugacity, you will have high concentration of this element in the magma. But if you get equilibrium of the oxygen fugacity, this oversaturate metal will form the nugget face. When the nuggets are present, people have thought of the method to deal with the signal. One of them is called the trough analysis. Let's say at this laser signal, these spikes here may indicate the nugget, and we don't want this part. So we only take the lowest part of the signal to filter the nugget signal. But the disadvantage of this method is that you lose most of the analysis time, and it's just a compromise. So we need to suppress the formation of nugget to solve the problem from its root. So I have tried a lot to solve the problem. I add titanium to my melt composition, and also center the starting material in reducing environment and pre-control the atmosphere at the beginning stage of my experiment. These two will give the sample more time to equilibrium in the reduced environment, and cannot have this oversaturate amount. And also I found that by prolonged experiment can also help. Here are the two diagrams showing the effect of experimental time. As you can see from the left one, if I have just 8 hours experiment, these spikes are pretty obvious. And if I have long experiment, the flat plateau of signal shows no nugget. And by comparing these two diagrams, you can also see that if I only use the trough of the signal here, the concentration is still a bit higher than it should be, which means the previous analysis might have some wrong data. The following results I'm going to show you are all done at the 1 atmosphere furnace, which is the ambient pressure. With this apparatus, I can control the oxygen fugacity and sulfur fugacity very precisely and to untangle their effect. Here are my results. The error bars are standard deviation of measurement, and the red dots of my study are very consistent with the previous studies. And these spots follow a straight line, which indicates the dominant species of gold in magma is gold 1+. Here I run 2 series of experiments to see the effect of sulfur. The red ones are at a bit higher oxygen fugacity, and you can see for both series of experiments, the sulfur can increase the solubility of gold, and the effect of sulfur is more severe under reduced condition, because the sulfur can dissolve more in reduced magmas. So to follow on my research, I would like to do more high pressure experiments and also do some hydrous melt composition to see the effect of water in magma. All these adjustments is to simulate the actual situation better. So the last slide is my conclusion. The formation of nanonuggets can be suppressed. The solubility of gold increase as the function of oxygen fugacity. Gold 1+ is the dominant species, and the sulfur can increase gold solubility, and its decrease is more prominent in reduced conditions. And I'm happy to take any questions and comments. Thank you.
Thank you. It was a great talk. Does anybody have any questions? We've got a question from Anthony Burnham. How much gold concentration in magma controlled by source versus oxygen fugacity?
When we talk about source, it's like the source of pure gold and also sulfide, right? I guess the characters of different source can place a more severe role than oxygen fugacity, because the partition mechanism is different between the metal alloy and sulfide into the melt. Yeah.
Cool. We've got time for one more question if anyone has anything. No? Okay, we might. Thank you for your talk. That was
Thanks.
Great. We'll jump on to the next one, which is from Neng on spatial association between drainage systems and long wavelength topography.
Hi. Now we're just, yeah, can you hear me?
Yeah.
Yeah, I'm just share the screen here. Yeah.
Okay.
Thank you. Good morning, everyone. And I'm Nan, a PhD student from the Underworld Geodynamic group. And today I want to share a project that I'm still doing. It's about the spatial association between the rivers and the long wavelength topography. The inspiration of this project it comes from the phenomenon that the river system out of equilibrium with the long wavelength topography around the world especially in some active tectonic regions. Here I show the topography with different wavelengths in the largest collision zone, the Tibet. As we all know, in a very refined resolution, the rivers will run through the topography from the high elevation areas to the low elevation areas driven by the gravity. But when compare its behaviors from with the long wavelength topography, it's a totally different story. So is there any correlations between the rivers and the long wavelength topography is what I want to figure out. Some past researchers will give us many insights about how the surface is formed. It's shaped by the integrations of the surface processes, tectonics, and mantle dynamics. And some studies show the different some direct links between the rivers and tectonic deformation and mantle convolution. And here are two typical related studies. One shows that the plate tectonic strengths may mainly control the drainage patterns in the New Zealand. In another word, the tectonic events happen there may to west the rivers. Another paper shows that the characteristic form of the drainage systems that it can show the topography domain association with the mantle plume. And these studies are very insightful, but haven't told us the real links between the rivers and topography or the factors behind the topography. So in this project, I want to find out the correlations between them, if there are any kind of the correlations, and try to better quantify the correlations. So how to do that? The one proxy matrix called the conformity factors may have the potential to be the base for resolving the relations. It's a simple and clear concept proposed by Black de Perro in their 2017 paper. It's for describing the drainage conformity with the topography. The conformity factor here is defined as the median cosine delta, and delta is the angles between the river drainage direction and the downslope directions of the topographic expansions. Here we define the lambda zero as cosine delta and their delta as delta median to do the distinguish. And it's very easy to understand, like its values is range from -1 to 1, and when their values is 1, it means that the river orientations and the downslope directions is the same. And the right figures here show the lambda median from their paper. The analysis, the drainage patterns on all three bodies, Titan, Mars, and Earth. And they found out that the large rivers, which may record the interactions between the deformation and the erosion modification. So the conformity here, the rivers conform better to the long wavelength topography on Titan and Mars than on Earth. So how to calculate? It's very pretty simple. Firstly, to compute the azimuths of the river orientation. The river data we used here is called the DRT data. It's from the hydro shears and hydro 1K to basically river data, and based on the dominant river tracing algorithm to upscale them. It contains the information of the flow directions and saved as like D8 angle values. The values 1 to 8 here denotes the river orientations here. And based on it, we can extract the main strings in the network. And then we can recalculate the azimuths of each river points. And the digital elevation data for calculating the gradient of the topography is the Earth 2014, and it's a 5-minute topography model. We can use some tools to processing the spherical harmonic coefficients to get the topography with different spherical degrees, like the figures showed here is two topography with two different harmonic degrees. One is 2000 and another is 20. So here is our result, the global conformity factors of the rivers and topography. Actually, we can barely tell what's the spatial patterns here, and that's why we need some further analysis. So how to do the regional patterns, how to find them? The one way is to divide the global topography into different regions. And here we can rebuild the tectonic regionalization from the the models here. And we can select three main kind of regions: the stable continent region, the arcs, and the orogons. And the arcs, orogons here is are the active tectonic plate regions. These two regions are the active continental moraines, where the two tectonic plates meet each other. And here are the results, the conformity factors, median. We can see from the figure that the general patterns here is conformed better to the long wavelength topography in the organs and the stable continent regions than the global Earth or arcs. These are the projects that I so far have done, and the results here leaves more questions to figure out. Some questions are like why the conformity factors of arcs are organs show the different patterns, because they are both active tectonic regions. And what about other regions? For example, some like the extended crest regions. And the rivers, we all know that is running through a bounding zone. So what about the patterns in the boundaries of these regions? And the codes and Jupyter notebooks available on the GitHub. So if you are interested, you can take a look and have a try. Thank you for listening.
Thanks, Nan. That was a great talk, really interesting. Does anyone have any questions? A couple of minutes. We've got a question in the chat, name from Anthony. Is there any link between lithology and CF?
Actually, there are some links between the lithology and the conformity factors, but I haven't taken that into consideration, because when you consider about the theology, it's like more refined resolutions there. You need to consider about the like the shorter wavelength influence. So that's a bit different here. But so the first thing like I do here is to find out the tectonic regions, the different tectonic regions. Actually, they have different lithology. But when you consider about more difference there, they may be need more case study, more refined resolution study.
Awesome. There's one from Matty. Any idea on validating the results?
Thanks, Marty, and it's a good question. For now, I haven't to think about it, because that's the project that's still doing here. And I think the result here maybe have the potential to show the correlations, but maybe it's not the right way to do that.
Maybe next year we'll be able to. Awesome. Well, great talk, Neng. Thank you for that.
Thank you.
We're gonna have a quick break. So quick break till 11:20, we'll come back. But just before we go, any academics that listened to those talks, if you could fill out the judging sheets and send them through to me, that'd be great. And if you have any leftover from yesterday as well, we only got a couple, it'd be great to get a little bit more feedback from those talks as well. So thank you. We'll see you in 20 minutes. All right, everyone, we might get started for our afternoon or after morning break session. First off, for the student talks, we've got Josue talking about ocean currents and our changing climate. Josue, are you there?
Yeah, I'm here.
Awesome.
Okay, let me share my screen. Can you see it?
Yep.
And you see it moving now?
Yeah, it's spinning.
Cool. Should I start or?
Yeah, let's start.
Cool.
All yours.
Well, I'm Josue. I don't know if you can see me in the camera because I cannot see anything except from my screen. So I'm in my last year of my PhD, and I'm in the CFP group, and I will be talking today about ocean currents and our changing climate. So as Guadalupe pointed out earlier, we already know that sea surface height has increased. So what I'm showing here is an animation of sea surface height for the early beginning of the satellite record. So from 1993 to somewhere in 1994. And there's a lot of features that you can see in the sea level. So you can see a lot of roughness on the sphere. Obviously, this sea surface height is not a scale. It's amplified, so you can see it. But there's a lot of small scale that's really hard to see. And overall, during the satellite record, we know that the sea surface height has been increasing. So that's what I'm showing in this time series on the right. And it's increasing. It depends on which kind of estimate you see, but it's increasing at a rate of like a couple of centimeters per decade. And anyway, moreover, like an important thing is that we can decompose this field into the mean field and the time varying component of the field. So that will allow us to see a bit better all these small scales. So basically, this is the equation. This is a really simple equation, but basically it's decomposing the sea surface height into its mean and its time varying component. So once we do that, we get this mean field, which is static. It's basically picking the mean value of this time series, which is highlighted here in cyan. So you cannot see much, except that you can see some jars, perhaps, or some regions where you have large gradients, or you can see some steps. So for example, here, if I can go back a bit. So for example, here you can see this kind of yellow region here that is surrounded in the north by a bit more reddish, a lower sea level heights, as well as in the tropics. And that's basically one ocean jar. It's important for the circulation, and more importantly, and this will be more relevant a bit later, there's boundary currents associated with these gyres. Perhaps that will be a bit more clear in here. So here, what I have is the time varying component. So in this case, the time varying component is basically all the wiggles once I subtracted the mean. So that's what the sign line here is as well. And now here you can see a lot of things. You can see a lot of small features moving around. You can see a lot of things in the equator that propagate really quickly. So it's a really dynamic field. You can see, perhaps here, if I stop it, you can see like some of these bombs that screwed out of the sea surface. We call those coherent eddies in oceanography. And they're really important, and this might be a bit more clear later. They're really important to transport tracers as nutrients, temperature, salinity. So they key on how they, how they are key in the ocean dynamics. So they can control regional climate in a sense, and they can control even the global circulation of the ocean. So if I go to a bit more of equations, so from that field, from that sea surface height, we can compute velocities. I'm not gonna go really in depth on this because it's a lot of maths. And this is, I promised the last couple of equations that I will show. From these velocities and from this sea surface height, we can translate to energy. And that's what I've been focusing most of my PhD on. So what I've been looking at my PhD is the kinetic energy of the ocean and how that has evolved with over time within the satellite record. So what I'm showing here is the kinetic energy. It's a logarithmic scale. It's really important to point out that the equators are really energetic. But here as well, where I highlighted before that we had these gyres, we also get these really strong currents, which are the boundary currents. I don't know if you can see those wiggles. Like a lot of these round features that look like rings, they correspond to eddies. And there's a lot of other wiggles that we commonly call meanders or things like that in oceanography. But if I let this play, so now here we're looking at Australia. You might be aware, might not be aware, but this is like the East Australian current. There's a lot of eddies. Perhaps if I play for a bit, there's a lot of eddies that are generated constantly there. That region is really important, and I'm sure Jess and a lot of other people will agree that that region is really important, and that current is really important for the corals. But also, so basically this is the kinetic energy, and if I do a global average of this field, I don't really see much, and I will briefly explain why, but oh, sorry. Well, and the reason to that is mostly because of the equator. And it's an ENSO effect in the signal. So if I go to, yeah, so it's an ENSO effect in the signal. So that's why we have these two large peaks in 1997 and also in 2015. And if we look, so now what I'm showing in this map is the kinetic energy trends over the satellite record. As you might observe, I start here with Australia, and there's like this large increase of kinetic energy, which is basically the currents of the ocean in the East Australian current extension. Oh, sorry, in the East Australian current. And if I let it display and I look now into the Southern Ocean, which was the first part of my project, you will see that there's a lot of red. So like the boundary currents are red. This is the Agulhas current. This is the Maldivian current. And like overall, even though this is a bit unsaturated, most of the Southern Ocean is red. There's some spots that are blue, but the overall trend, the increasing trend is positive. And as you might notice, like all these really strong reds are usually localized where boundary currents exist. So now I'm going into the Atlantic Ocean. And again, here's the Gulf Stream, which is a really important current. That's the current that provides heat to Northern Europe, and that's the one that controls that they don't get freezing colds. And perhaps to see it a bit clearer, this is basically the same map as before. It's just like all shown. And the energetics of the ocean having, I mean, if I do a average over the whole globe, the kinetic energy has increased. And this has been linked to the strengthening of the winds and changes in thermal gradients. However, during the last year, I've been trying to find a dynamical explanation. I haven't been able to. And I think that's mostly what I have. So any questions?
Awesome. Thanks, Josue. I always love all your images and the videos. I wish I could do that for my stuff. Does anybody have any questions? Ooh, stop it.
Can I ask one question?
Yeah.
Yeah, first of all, thank you. It was very nice talk, and if there was any animation, we enjoyed the talk more. But I didn't get why you have that increasing trend on 1990-ish and 2016.
Oh, why? I don't know. Why these peaks?
Yeah.
So those peaks are connected to ENSO. I haven't really looked like El Nino events. I haven't really looked too much in depth on why. I mean, the hypothesis that we currently have is that there are tropical waves. So when we have ENSO events, the horizontal temperature gradient of the equator changes. So then you have more propagating waves. And I think that's what we're seeing there.
Mm-hmm. But you haven't checked El Nino yet, huh?
Yeah, but I haven't checked El Nino in depth. Yeah.
Okay, thank you.
Awesome. We might leave it there, Josue, and we'll move on to the next talk. Thank you. Next up, we have Tung, who's talking about using deformation mechanism maps to interpret results from forced oscillation and microgroup testing. Did you want to share your screen?
Thank you. Because what should I do? Yeah. Okay. Yes, you can see it now.
Yeah, all good.
Yeah, okay. I'm gonna share my recent work about using deformation mechanism map to interpret the mechanical testing results. In the title here, the forced oscillation and the microgroup testing are two kinds of mechanical testing. We apply oscillating torque to the sample at high temperature and pressure in forced oscillation. And for microcreep, we apply constant torque. These are the results from forced oscillation testing. They are shear modulus at different temperatures and different periods. As you can see, when the temperature is higher than 700 degrees, by the way, this is a sample of stainless steel, which is not a rock sample, but olivine has similar thermomechanical properties. So when the temperature is higher than 700 degrees C, there will be a transition from elastic properties to inelastic properties. The manifest of that is the frequency dependence of shear modulus. For olivine, that is also related to the boundary between the lithosphere and asthenosphere. Yeah, so overall, that's a measurement of shear modulus at different periods and different temperatures. These are the results from microcreep testing. As you can see, similarly, when the temperature goes up, there will be a time dependent of strain, which is also a manifest of an elasticity. So my work here is to use a method called deformation mechanism map to interpret those results. I should start with explaining this concept. What is deformation mechanism map? I found I might be terrible at explaining things, but I'll try. So for deformation, there are two kinds of deformation: fractural deformation and plastic deformation. For people studying Earth's crust, they may be more interested in fractures. My focus is plastic deformation. We all know this figure, which is the atomic potential energy between two atoms. And when we apply horizontal shear stress here, the atoms will rupture their original bond and fall into a neighbor potential well. And we can theoretically calculate the stress required for gliding the whole atomic plane. And it turns out to be a third or a thirtieth of shear modulus, which is a great value because shear modulus is really at the level of tens gigapascal. But that has been approved to be wrong in experiments. Experimentalists only need to use 10 to the minus 4 of shear modulus to plastically deform crystalline material. So the conclusion here is that deformation must be facilitated by some deformation mechanisms. The most famous one is dislocation movement. So when we, this is an example of edge dislocation. When we have an extra half plane here, once the shear stress is applied, we don't need to shear the entire atomic plane, but only this half extra plane here. So we rupture the old original atomic bond and then form this new one. So only a small group of atoms are involved in this process. This is another one. This is called vacancy. When we apply shear stress, only need to move one atom to fill this vacancy. So very small amount of stress is needed. And some other defects could also disturb the distribution of potential energy. This one is called interstitial atoms. We have an extra atom somehow falls into an awkward position here. So it disturbs the potential energy. And this one is grain boundary related. When we apply stress to the sample, there will be a gradient of chemical potential. And that potential will motivate atoms to move. And so this one is grain boundary related. And for all those deformation mechanisms, we use a kind of constitutive relation to describe them. The relation is between stress and strain, or strain rate. And the constant here, it varies with different mechanisms, is a function of temperature, time, and microstructures. It is more complicated than what it is now, but I'll just simplify this. So to construct this map, I use temperature as input and the normalized stress, which is stress over shear modulus. Those two are my inputs. I take this input into different constitutive relation, and I have an output as a contour map of strain, different kinds of strain, total strain, and individual strain from different mechanisms. Here I focus on dislocation related mechanism and grain boundary related mechanism. Those are two major players. This is map of total strain. So the x-axis is normalized temperature, and y-axis is normalized stress, shear stress over shear modulus. At low temperature, when the mechanical behavior is purely elastic, this contour line is horizontal. It just simply follows this, that's shear stress over shear modulus. And when the temperature increases, those deformation mechanisms start to kick in, and the contour line becomes not horizontal anymore. And the transition temperature occurs at 0.7 of the melting temperature, which is about 900 degrees C. So in the fossil oscillation testing, this temperature is slightly higher than the transition temperature shown in the fossil oscillation. So possibly currently we are missing some mechanisms for the transition from elastic to inelastic regime. And microcreep testing, which is not sensitive to this transition, itself is more consistent with deformation mechanism map. Those two individual plots for the individual mechanisms. This one is for dislocation related strain, and this one is for grain boundary sliding related strain. It can be seen that at very high temperature, dislocation related strain is much more profound than grain boundary sliding. And when the temperature is getting lower, the two strains becoming comparable. So again, in the fossil oscillation data, that means when the temperature is higher than 1000 degrees C, those frequency dependence of shear modulus is mainly dominated by dislocation moment. And when the temperature is getting lower for this area, it's possibly because of the combined contribution from dislocation and grain boundary sliding. So yeah, for earth scientists, I guess our interest is to apply this map to mineral physics. And the duty of our mineral physics study is to experimentally constrain the relationship between seismic structures and physical states. And to do this, we do fossil oscillation testing as a simulation of seismic wave propagation. But our this is challenging work, and the problem here is that the grain size of our sample is at the scale of 10 microns, which is much smaller than natural sample. So here we need to have a robust understanding of deformation mechanisms to extrapolate our data to seismic structures. And we could use this deformation mechanism map to help us to better constrain the deformation mechanisms, and then better interpret the experimental data and better interpret the seismic structures in the upper mantle. Yeah, that's all. Thanks.
Thanks, Doug. That was really interesting. We don't actually have any time for questions for this one, but if anyone does have any questions, just pop them into the chat and maybe you can answer them as we're going through the next talk. Cool. So next up, we have Caleb.
Not yet.
Caleb, and I'm going to let you introduce your talk because I don't think I could pronounce some of it. So.
That's fair enough. Just need you to stop sharing your screen.
Yeah, can't find my mouse. One sec. There you go.
Okay. Okay, well, thanks, Jess. And thank you all for sticking it out and making it through to the second last talk of the day. So I'm Caleb and I'm from paleobiogeochemistry, and I'm going to be telling you a little bit about tracing the evolution of early archaeoplastida throughout the cryogeny and glaciations. Archaeoplastida are really just a group of eukaryotes. They comprise of things like red and green algae, the land plants, glaucophytes, like in the picture here. And these really form a major group of eukaryotes, but this was particularly so in the geologic past. And so understanding their early evolution really helps us understand the evolution of eukaryotes as a whole. So looking back in time, the Precambrian was really a pretty unrecognizable place. There was no life on Earth, there was no oxygen around, and the only things living were these things like these little cyanobacteria, these single-celled organisms. And these really held the reins on Earth's oceans for some 3 billion years or so. But when we look at Earth's oceans today, we see that they're more or less dominated by these eukaryotes. And these, I guess, these more complex membrane organisms. And so I guess the question is, when exactly did eukaryotes take over? And as I hope to show you in just a moment, knowing precisely when eukaryotes took over is vitally important in understanding how and why they took over. And this is important to know because this was the moment in Earth's history where the Earth transitioned from something that looks like this picture in the background to the Earth that we know and love so much today. So how do we go about tracing this ecological shift, especially when these organisms didn't really have skeletons that could fossilize for us? Well, we use things called biomarkers, or rather the tough molecular remains of these organisms. So organisms like this algal and bacterial cell have membranes, and these membranes are full of really stiff and tough membrane lipids that give the cell its structure. And these take the form of sterols in eukaryotes and hopanols in bacteria. So when these organisms die in the water column, they sink very, very slowly. And as they're sinking, about 99% of the biomass is actually recycled back into the water column. But the really tough molecules, like these lipid membranes, these sterols and hopanols, actually make it to the sea floor and are buried. When they're buried, they heat up. And as they heat up, they lose their double bonds and their functional groups. And so what we're left with, I guess, are these sort of carbon skeletons of the precursor molecules. And although some of the biological information is lost at this point, there's still lots of information we can get out of these things. By taking the ratio of steranes to hopanes, it gives us a sort of a first order indication as to the relative amounts of eukaryotes versus bacteria in the geologic past. So just as biomarkers can be domain specific, they're also taxa specific. These are the 3 most abundant steranes, so eukaryote biomarkers, the C27, 28, and 29 cholestane, ergostane, and stigmastains. And these differ by no, a methyl, and an ethyl group on the C24 position. And by and large, the groups responsible for these are the red algae, fungi, and the green algae, although the ancestral fungi probably weren't the primary producers of C28 in the geologic past. So we can take a look at the ratio between these trifecta steranes, as particularly looking at the C27s and the C29s, and this gives us a bit of an idea as to the relative abundance of each of these communities living in the geologic past, or particularly, we can trace the waging war between rhodophytes, red algae, and chlorophytes, the green algae. So what does this look like in the geologic past? Well, works from Brox et al., I guess they found, when you sort of take at first glance, there are these, I guess, 2 distinct worlds. There's, and I guess they're separated by these really intense glaciations. And indeed, when we look closely at the data, we see that the pre-glacial world, the pre-cryogenian world, shows 100% C27 cholestane abundance. And this continues into the aftermath of the Sturtian glaciation. But then in sediments from Oman, just prior to the Marin snowball, we allegedly see the appearance of chlorophytes, given the explosion of C27s in the trifecta. However, in the cap carbonates, we allegedly see the appearance of the primitive signatures coming back into our sediments again. And then sometime in the very, very early Ediacaran, we see the appearance of cholestane with a flux of sterane-hopane ratios, remembering that this is a sort of indicator of how well eukaryotes are doing. So the inference being that it was the appearance of these chlorophytes that really led to the success of eukaryotes as a whole.
And it likely did this by, I guess, supplying the deeper ocean with nutrients and oxygen. They were bigger and they sunk better. But this first set of stripes, this is entirely based upon a single solitary sample from Oman. And these were really just a handful of cuttings, little chips at the bottom of a core tray. And they're highly susceptible to contamination. And no inside-outside separation was done, just a quick dip in some solvents and hopefully that'll do. And so for these reasons, among others, we would like to propose a slightly different model on the rise of algae. We would like to propose a single-step transition happening sometime in the very early Ediacaran, but post-glaciation and not during the glaciation. So how do we go about proving this? Well, simple, right? We just get sediments pre and post snowball and we look at the biomarkers inside. Well, right there is the problem, because glaciers erode and they erode a lot. And so there's very little pre and post snowball stratigraphy around the world. But late last year, I discovered some sediments from the Western Officer Basin that might just help us out a bit. The Vines 1 drill core is totally unique in the sense that it contains diamictites from both snowballs in contact with each other. And wedged in between these tillites are these finely laminated intercalated shales. They're not very organic rich, but the biomarkers are there. And so for the first time, we're really able to trace what life was doing throughout the snowballs. And when we do that, this is what we find. Separation, careful separation of the interior from the exterior fractions shows that on the interior fraction, we contain the presence of cholestain, but in the exterior, and also no ergostain and no stigmastain. But on the exterior fractions, we see the presence of all three of the trifecta. And so this really highlights the importance of careful separation techniques during these sorts of studies. And so also looking at the Sterine-Hoppein ratios, we see they're extremely low, 1 to 2 orders of magnitude beneath typical Phanerozoic levels, which are given by this yellow line here. And when we compare these to other sediments from the, and just reminding you that the Sterine-Hoppein ratio is an indicator of how well eukaryotes are doing relative to bacteria. And when we compare these Sterine-Hoppein ratios to other Ediacaran sediments in the same basin, just a bit further east in the Eastern Officer Basin, we see these low Sterine-Hoppein ratios continue into the early Ediacaran. And then I guess there's a sort of general progression towards higher values, reaching typical Phanerozoic levels by the Cambrian. So I guess the idea is that there is a general sort of diversification and then proliferation, and not this sort of boom bust situation, which the former two-step model would have us believe. So deconvolving all these signatures, we believe a reprisal and our understanding of the rise of algae is in order and should now reflect a one-step transitional model like this, with the rise of chlorophytes occurring sometime in the very early Ediacaran, which ultimately led the way for eukaryotes and the proliferation of Archaeoplastida in the whole. This isn't finding biomarkers from inside the snowballs themselves doesn't exclusively prove this model. It doesn't disprove that prior to the snowball was when we had a radiation, but it certainly stacks more evidence against it. And so the takeaway messages, thinking back to our original question of what was life during the snowballs, is that bacteria remained the dominant life form throughout the cryogenian glaciations, and rather these chlorophytes, these complex eukaryotes, emerged and proliferated after the cryogenian glaciations, not long after, but after. And so, and we're closer to finding the rise of algae, but an actual section is still yet to be discovered. And that's all I had. Thank you.
Awesome. Thanks, Caleb. Really interesting talk and a great overview, because I had no idea what you guys did up there. So really good. We don't actually have any time for questions at the moment, but if anyone does have questions for Caleb, just pop them in the chat, and I assume you can answer them from there. That's all right. Next up, we have Buse, who is going to, I'll let you introduce your talk as well. I'm just going to turn off the recording.